I get a nasty phone call from my boss, I'll know who went and sent the information. Oh God, my boss is so used to me now, I think he just shakes his head. Okay, so what we're looking at today is how to calculate arc length. At least the first part of today is going to be that. Hopefully we'll get onto other stuff. That's essentially the formula that you use to calculate arc length. It's the square root of the first thing, the x component squared, y component squared, and z component squared. And the space curve in at least this form would be f of t, g of t, and h of t. And we talked about last time that there are three typical algebra situations that you can get. One is that this is a number, which is very nice. Got that with the helix that we did. It's a perfect square, or it's if it ends up eventually being a substitution. So I'm going to jump right into question 2 and show you one that ends up being a perfect square. So we're being asked to find the arc length for this space curve. And it's going to go from t equals 0 to 1. So the arc length is going to be the integral from 0 to 1. This guy, that mess says 4t, so differentiate it, you get 4 and you square it. Differentiate t squared, you get 2t and then you square it. And differentiate this guy and you get 3, that's a half t squared, and then you square it. And I'm going to square these things and change the order a little bit, putting the highest power first. You get that. Now, these questions are really only going to be doable if this is a perfect square, right? Would you agree it's not a number and there isn't a U sub in the world that will save you, right? So we know it's not a U sub. We know it's not a nice number because it's obviously got t's and t squares in it. And so when that happens, you will assume that it must be a perfect square. But the problem is that the perfect squares that you're going to get are not things like, oh, x squared plus 6x plus 9, right? Nice quadratics that you're used to. So when you put them in order, highest power to lowest power, as I've done here, right? There is a way of finding out what this is a perfect square. Take this guy, 1/4 t to the 4. If you take the square root of a quarter, you get a half. If you take the square root of t to the 4, you get t squared. Now this number is 16. If you take the square root of 16, you've got 4. Can you trust me that if you FOIL this out, you get back to there? So notice what I did. I just basically said, okay, take the square root of each of these guys, take the square root of whatever's over here, boom. Check it out by foiling, but it does work. And the reason I know this is going to be true is because they're only going to give you questions where if there's 3 terms in this square root, it's going to be a perfect square world, right? And that's the most common answer that you're going to, or most common situation that you're going to deal with. That means that the arc length is now going to be the integral from 0 to 1, but the square root of a square cancel each other out. Do you see that that integral is now doable, right? Integrations with square roots are intensely horrible. And if you can get rid of them as you can in this question, it's good. So I'm going to add 1 to the power, divide by the new power. And the 4 is going to get me 4t. And I'm going to evaluate it from 0 to 1. And that's going to get me 1/6 plus 4, take away a whole load of nothings. And that's going to get me 25/6, I believe, which actually is correct. Are we good with that? Right. So perfect square. Let's pick another one. This is question 4. Again, it's an arc length question. We're finding the length of this space curve, which is the square root of 2t. This one's in terms of I, j's, and k's, but I'm not doing that. I'm doing it that way because it's easier in my brain. And it's going to go from 0 to 9. Okay. Then the arc length is integral from 0 to 9. Square root. The square root of 2t, when you differentiate it, is the square root of 2, and then you square it. The derivative of e to the t is e to the t, and then you square it. The derivative of e to the negative t is negative e to the negative t, but then you square it. Square root of 2 times itself is 2. E to the t squared. What power of e is e to the t when you square it?
E to the 2t.
Correct. And can I tell you that that guy there is going to be e to the negative 2t? So far, so good. Now, do you notice that there's 3 terms? That means this is going to have to be a perfect square. But you must put them in order. And what I mean by that is, in this case, the biggest power is e to the 2t. The number 2 is in the middle, and e to the negative 2t is at the end. Does that make sense that this is an order of powers? So negative powers belong at the end, positive powers kind of belong in the middle, and then everything else goes there. And I'm saying that is a perfect square because it is. The guys you're going to use come from here, come from here. Okay. What will the e to the 2t give me when I do it here? What's the square root of e to the 2t, in other words?
Is it just e to the t?
Yeah. Half the power. Half the power. Are we good with that? Now, do you want to trust me? Go and foil it out in your own time. I bet you it's equal to that when you're finished, right? So this is perfect match, which means that we now have the integral from 0 to 9 of e to the t, e to the negative t, dt. Would you agree that integral is doable, right? You can find the integral of that relatively easy. And I'll let you, you could finish that off your own time. Oh, note to self. Let me write that down. I found one of those questions that I told you yesterday that I don't want to find. You know, the ones that have square roots that don't work and you have to go to the back of the book. So that's question 5. A little note to self to kill that one. So question 5 is going to be dead in a second. So if you hold off while I kill the poor thing. It's not that you couldn't do it, but you end up, you just have to do it by looking up what the integral of secant t is, and it's not very pretty. And you want to avoid things that aren't the usual kind of question. Okay, almost done. Okay. Let's go back in. Hopefully I won't have any more of those. So one of them sneaked by me. I thought I'd caught them all, but I was wrong. Right, arc length, arc length. Okay. Right, I think we're done with arc lengths. I'm looking to see if there's any more. Oh, okay, here's one. So we're doing a space curve. 8t, t squared. Actually, I've done that one. What am I talking about? At least I've done one like that, have I? Maybe not. I take it back. Okay. Arc length of this guy, and we're going to do it from 0 to 1. So it's going to be the integral from 0 to 1. Differentiate this guy is 8, and then you square it. This guy is 2t, and then you square it. And this guy is 1/4 t squared, then you square it. This guy times itself is 1/16 t to the 4. This guy gets you 4t squared, and this guy here gets you 64. So we square these guys, and then I put them in order while I was doing it. So far, so good. This guy and this guy, right? Notice they're in order. This case, t to the 4, t squared, and the constant. Okay. What goes in here?
1/4
t squared.
Great. And that one's easy. Add 8. And so you end up with the integral from 0 to 1 of 1/4 t squared plus 8 dt. Can I just leave it there and you could finish that off anyway? It's pretty straightforward integral. It's arc length, equation 5. So let's do an impossible one and show you a kind of workaround for it. So this one is not going to be a perfect square. It's not going to be a number. It's not even going to be a U sub, although I haven't managed to find one of those yet. It's just going to be an answer that is not doable algebraically. So the arc length is the integral from 0 to 1. The derivative of this guy is 2t, and then you square it. The derivative of that guy is e to the t, then you square it. And the derivative of that guy is cosine t, and you square it. And I've deliberately chosen a question where it's pretty obvious you can't do any of the techniques that we've talked about. But you can do it numerically. What do I mean by that? You can get the area of things using your calculator, and you will know that you're in this type of question because they will have, let's see what the phrase is, use a calculator or something, right? So the minute you see use a calculator, you know you're going to do basically this. So how do you set it up for your calculator? Let's go. Don't know if you've done this before. I'm assuming that you have. Have you all used your calculator to find areas under curves, which is what an integral is? No? Let's show you how it works. You type this guy in. So you go square root of 4, we'll have to call it x, but it's no biggie, 4x squared plus e to the power of 2x plus, to get cos squared t, at least on my calculator, you have to do a little bracket. You put the cosine of x inside it, and then you square it at the end. So that should be this fella, right? Including the square root. I'll make sure that I'm in radians, which I'm glad I checked, because for calculus, things should be radians. And then you go and you do second calculate. And right down at the bottom, do you see the one that looks like a little integral symbol, number 7? You hit enter. And I forgot something, which I hope I haven't killed it. I forgot to put in my window, so it's from 0 to 1. Now I should be able to do it. Second calc, choice number 7. If you hear a pig being killed, oh, okay, lower limit is 0, upper limit is 1, hit enter. I should have done a zoom effect, but don't worry about it. There's the answer. 2.215743. Do you see it at the bottom? So roughly, the integral from 0 to 1 of this ugly square root is about 2.22 to 2 decimal places. Are we cool with that? The reason that's a band there, if I do my Y guy, if I do zoom 0 to zoom to fit, you'll see what the curve looks like. I'm not doing anything different, it's still going to be 2.21. And then I can do second calc, choice 7, lower limit 0, upper limit 1. There it's finding the area under the curve, which is still 2.22. Excuse me. You are a pain. You are. Cut it out. Right. Are we good to move on? So if you see, use your calculator, you're not going to do any, that won't be a perfect square, you just do it numerically. And I think that's question 5. And I think there's another one that's kind of like this. Question 4 then. Right, it's question 5, but there's probably another one somewhere. I just can't find it right now. Oh, there we are. I found it. Question 5 and 6. Well, that was arc lengths for the time being.
So I have a quick question.
Yes.
For the calculator, do you keep it in degrees or radians for those?
Radians, right?
Radians.
So a general rule for calculus is always radians. Right. So what's next? Well, it's not that we're going to be doing too much of a different stuff, but we are going to do a guy called curvature. So the curvature of a space curve. So can you imagine this is your typical space curve? The concept of curvature is really a number that tells you how curved something is. Try to think of a better phrase. To give you an example of what I mean, would you agree at this point here, it's quite a sharp curve, and here it's a much gentler curve? Do you get the idea of, you know, if you were in a car, right, and you were going around a really sharp curve, right, that would have a high curvature, right? And if you were going a very gentle curve, that would have a small curvature. So curvature is a number that tells you how curved something is. So if you go at one extreme, you have a straight line. The curvature is called kappa t. So it's a Greek letter that looks like a K, but it's actually pronounced kappa. But non-Americans, you'll probably call it kappa or something just to annoy me. Right, it's kappa. Since you don't know that letter, aren't you all going to call it kappa now, right? Great, nobody's heard of that letter until I did it today. Now, a straight line, any point on a straight line has a curvature kappa of 0. Would you agree that's as uncurved as anything could be, would be a straight line, right? Very uncurved. And then you might have a gentle curve. And let's say at one point, so that point there, the kappa might be 2. And then can you imagine a really sharp curve? That might have a kappa of say 100. It is possible for something to have a curvature theoretically of infinity. But it's a weird thing. Anybody want to have a guess at what kind of thing, and I'm calling it a thing, that has a curvature of infinity? And it's not obvious, but once I tell you, you might think it's obvious.
Is it a sphere?
Well, we're talking about a curve, so we can't go into 3D, although a curve can be in 3D, but it has to be like a piece of wire, right? Kind of.
I'm going to take a totally random shot in the dark and just say the very, very middle point of like a Fibonacci spiral, when it's all the way in the middle of a spiral and it's super tight.
Yes. Or
Seriously?
just a single, yeah, or a single dot in space. A single point in space has an infinite curvature. Right? You can't get any more curved than just one point in space. It's a very weird thing, but that's it. So all curvatures are positive. 0 is for straight lines. The bigger it is, the more curved it is. So if I'm talking about a space curve, at different points on that curve, isn't the kappa going to be different, right? So can you imagine at this point here, kappa could be 10. At this point here, kappa is 0. At this point here, isn't it almost straight? So not 0, sorry, 3, say. At this point here, it might be almost straight, you know, so it's a kappa like that. So finding the curvature of a point is very useful. It's a thing that people who are interested in the motions of objects would find a useful number. Now, if you're wondering where the heck do they get the kappa from, let's show you what it does. Let's suppose this is my space curve, and I'm interested in the curvature at that point there, right? What you do is you find a circle that has the same curvature as that point. You imagine circles are good ways to measure curvature, right? And you find the radius of that circle. And kappa, the curvature, is 1 over the radius. So if you're wondering where that came from, can you imagine at any point on a curve, you could find a circle that's got the same curvature? And if that circle had a radius of 10, kappa would be a 10th, right? If the radius was 0.1, can you imagine a circle with a radius of 0.1? Wouldn't that be a tiny little circle? Wouldn't tiny little circles be very curved? 1 over 0.1 gives you a kappa of 10. You see, it's kind of a reciprocal relationship. So that's what it is. How do we calculate it? Well, there are a number of formulas, but here's one of them. Kappa of t is the magnitude of the unit tangent vector divided by the magnitude of the derivative. Not at all obvious, and I'm not even going to vaguely even try and justify it, but can you just trust me that that'll tell you the curvature of a space curve? So it uses guys we know. Don't we know how to find the derivative and then its magnitude? Don't we know how to get the unit tangent? Differentiate that guy and get its magnitude. Great. So let's suppose I have a space curve. And I'm going to pick my favorite one to do it to. Do you recognize a helix like you were talking about? Here, right? This little helix doing its thing. I would like to find the curvature at any given value t. They're the hardest ones to get. If you're being asked to find the curvature at 1, right, kappa of 1 or kappa of 0, that's a little bit less work. But when you have to keep it general, it does get a little bit messier. So when I get the answer, it's going to go here. Do you notice that kappa is actually a scalar? It's a single number, isn't it? Because that's a magnitude, and so is that. It's not a vector. It's a 2t plus 1 kind of thing, right? It's not a vector. So I'll start off with our derivative. And our derivative is -2 sine t, 2 and 2 cosine t. And then I'll find the magnitude of this. And that's the square root of this guy squared plus this guy squared plus this guy squared. And that's 4 sine squared plus 4 plus 4 cos squared. Okay, style points. This actually simplifies really nicely, doesn't it? What do you get out of this? You get 4 plus the 4 in the middle. Are we comfortable or happy with the magnitude of the first derivative is the square root of 8? Okay. Now, I need to find that guy, because I need to find that guy before I can differentiate him, right? And we've got all the pieces, because isn't that guy 1 over the magnitude of this fella? Right, so we already had to use it. So we're kind of double dipping here. Now the derivative is this guy, so it's going to be 1 over the square root of 8, -2 sine t, 2 cosine t. And I should have called that 2 root 2, shouldn't I? So if you take this guy, you're going to get -2 sine t over 2 root 2, 2 over 2 root 2, that's what square root of 8 is, and 2 cosine t's over 2 root 2. Cancel, cancel, and you get negative sine t over root 2, 1 over root 2, and cosine t over root 2. And I'm not going to make any attempt to make that pretty. You can do that in your own time. So far, so good. I now have that guy. Well, the formula says differentiate this guy and then find the magnitude. So that's where I'm up to now. If you differentiate the unit tangent vector, this guy here will get you negative cosine t over the square root of 2. This guy here will get you nothing. And this guy here will get you negative sine t over the square root of 2. And the magnitude of this derivative is going to be the square root of negative cosine t over the square root of 2 squared plus nothing squared, and this guy also squared. If you square that, you get cosine squared t over 2 and a nothing. I don't know where that came from. And a sine squared t over t. Wait a minute, what do they two things add up to? They add up to a number. What number or fraction? 1/2. And can I call that 1 over square root of 2? Okay, curvature. The curvature is the magnitude of the unit tangent vector divided by the magnitude of the first derivative. And it's a 1 over root 2 and a 2 over root 2. Okay, so if I want to make that pretty, it's 1 over 2 times a root 2 times another root 2, and the answer is 1/4. In this shape, the curvature is always 1/4. And you might think, well, how can something always be 1/4? It's not that unusual. Aren't helixes the same curvature? If you look at them side on, don't they look like circles? So in this particular case, the curvature is the same no matter where on the curve you pick. So if you pick this guy, the curvature is the same. If you pick this guy. Now that guy might look much more curved than that, but that's because of orientation, right? If I turned this and you looked at it straight on, wouldn't a helix look like a circle coming towards you? And so at any given point, isn't the curvature basically the same number? Circles have curvature where every point on that circle has the same curvature, and the curvature is 1 over its radius. Are we good with that one? Yeah. Now, have you noticed that
last paper real quick?
Sure.
Thank you so much.
Have you noticed that when we're doing these calculations, there's a lot of square root stuff going on? You want the guy inside the square root to be a number or a perfect square. Because if it's not, the math becomes really, really, really horrible, right? Like half an hour for one question, right? So you're going to pray that that's the case. Now, they also give you in this set of questions unit normals to calculate, but I'm not going to do that because we've done them before. I'm only going to focus on the curvature. So let's pick question 10. We have a space curve, 4t, 1/2 t squared, and a t squared. And we want that guy, and we want to find its curvature. Right? So it's going to be the magnitude of the unit tangent's derivative divided by the magnitude of the first derivative. Differentiate this guy, you get 4. Differentiate this guy and you get 2t. Differentiate this guy, you get 2t. Magnitude of this guy is 4 squared plus t squared, 2 over t squared. 4 plus 1, 5t squared plus 16. Well, I guess we're in trouble. This is going to be ugly. Great. Of course, I have an advantage because I can cheat. You can't. So let's find the unit tangent. The unit tangent is 1 over that magnitude of the first derivative, in which case it's 1 over the square root of 5t squared plus 16. And the guy that we've got is 4t and 2t, which means that we now have 4 over the square root of 5t squared plus 16, t over the square root of 5t squared plus 16, all over 2t over the square root of 5t squared plus 16. Now we have to differentiate this guy, which means I'm going to have to differentiate that ugly term, and that ugly term. I'm going to cheat. If I knew the answer to this middle one, right, so wouldn't it be the quotient? No, right? And I got the answer to it. Would I really need to do much work to get the answer for this one? No. Wouldn't I just double whatever that one was? Now, that's not a lot, but at least it's something, right? So if you were doing it the real way, you do it by hand and so on. But I'm going to tell you what the answer is because I've got it in front of me. And it is going to be negative 20t over the square root of 5t squared plus 16 cubed. And then the middle one is going to be 16 over the square root of 5t squared plus 16 cubed. And the last one, not surprisingly, is 32 over the same guy. So they're all over this guy. And to find the magnitude, you take this guy and square it. You take this guy and square it. And you take this guy and you square it. And again, you're going to trust me on this one. It's 4 root 5 over 6, well, I'll write it down that way, that guy. You're going to have to differentiate each of these to get that. That's probably going to take you 5 minutes for that one, 5 minutes for that one. So it's 10 minutes to do that. You're then going to square them all. You're going to add them together and you're going to tidy things up. And it's eventually going to come out like that, which is amazing, but that's what it's going to come out like. And that'll take you another 10 minutes, say. So it's going to take you 20 minutes to do that one, which I'm glad I didn't, but that's what we would have got. And so to get the curvature, you just take the magnitude of this guy divided by the magnitude of that guy. So let's see what that looks like. I have a 4 square root of 5 over 16 plus 5t squared, that's the top. And on the bottom, oh, quite a nice looking thing, I guess. 5t squared plus 16. If you combine them, basically that joins this guy. And the answer is this fella over the square root of 5t squared plus 16 cubed. So the curvature of this fella is 4 root 5 over the square root of 5t squared plus 16 cubed. So if I wanted to know what the curvature was, let's say when t is 0, it would be 4 root 5 over nothing plus 16. So the square root of 16 cubed, which is 64. So it'd be 4 root 5 over 64, which would be root 5 over 16. And if I found the curvature, say at 1, it would be 4 root 5. Oh, 1's probably a bad choice, but I picked it now, so I'll stick to it. 5 is 21, so it'd be the square root of 21 cubed, which I'm just going to say dot, 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 right? Some ridiculous layer. Actually, it's not that bad, now I think about it. Basically, it's 21 root 21. It's not that bad. Right, so you can evaluate that original space curve. You can evaluate its curvature at any given point. And I'm looking at these guys. And they are really messy. So let's show you an alternate formula for calculating curvature. And the alternate formula is the magnitude of the first derivative cross product with the second derivative, all divided by the magnitude of the first derivative cubed. Now, I'll put below it the guy that we've just finished doing. They're quite different looking, agreed? Yet they both will give you the same answer. If you take the guy that I just pretended to do, which was this guy here, right? This one here would have taken about 25 minutes to do, that would be my guesstimate. Yeah. Let's see what it might look like on this second formula. So it's still a 4t, a 1/2 t squared, and a t squared. Right. To use this formula then, let's see. One of the good things about this formula is you don't need to worry about magnitudes until the end, right? You're just doing derivatives, which tend to be quicker, right? As long as they don't have really weird ones. So here goes, 4t, 1/2 t squared, t squared. You find the first derivative, 4, 2, no, t, and 2t. I'll write that again. So 4, a t, and a 2t. And you find the second derivative, which is 0, 1, and 2. Would you agree that's a lot cleaner? No weird square roots involved, right? Just differentiate, differentiate. Okay. Cross product coming up. If you take the first derivative and you do a cross product with the second derivative, you get I, J, K. The first derivative is 4t, 2t. The second derivative is 0, 1, and 2. You with me? Okay. So it's going to be so many i's, take away so many j's, plus so many k's. Cover that guy, you get 2t, take away 2t. Cover up that guy, you get 8, take away nothing. Cover up this guy, you get 4, take away nothing. You end up with 0, -8, 4. And that's the first crossing the second. Came out quite nice. So I need to know the magnitude of that cross product. So it's the square root of 0 squared plus negative 8 squared plus 4 squared. So it's the square root of 80. Our first derivative is this guy. I want to find its magnitude. And it's going to be 4 squared t squared 2t squared. I know I'm going through this, but I'm trying not to use your time up. It's that guy. So the curvature is the magnitude of the cross product of the first and second divided by the magnitude of the first derivative cubed. And that gets you square root of 80 over 16 plus 5t squared cubed. And the square root of 80 is 4 root 5. Would you agree it's the same answer? Would you also agree it was a lot easier? So here's a suggestion for you. When you are doing the curvature questions, pick whichever one of the 2 formulas I have given you, right? So if you want to do it using this formula, go ahead. If you want to do it using this formula, go ahead. So we'll let you choose. And the reason that there are 2 formulas is that for some questions, actually this one is less work than that one. And then for other questions, this one is less work than that. And if you're anything like me, won't you always pick the wrong one? You're always going to do this one when you should have used that formula, or you're going to use that formula when you should use this one. I think you should know after about 5 minutes whether it's going in a nice direction, like everything's coming out really nice, or it's 3 really ugly derivatives. When you see that, aren't you going to say, I'm going to do this now?